Imagine a smart greenhouse where temperature sensors constantly report data while water pumps and fans receive commands remotely. The key to this seamless interaction is MQTT's publish-subscribe architecture. Instead of devices talking directly to each other, they communicate through a broker, which acts as a central post office. Sensors publish their data to predefined topics, while actuators subscribe to command topics to receive instructions. This decoupling is powerful. Devices don't need to know each other's addresses or existence, they only care about topics. In this lesson, we'll configure the ESP32 to publish simulated temperature readings to a broker and subscribe to topics for receiving control commands. Along the way, we'll learn how to structure topics, parse JSO payloads, use event-driven callbacks, and manage reliable two-way communication. By the end, you'll be able to build a scalable communication pipeline essential for any serious IoT project. MQTT uses a topic-based system to route messages. Think of a topic as a mailing address, for example, home living room temperature. When the ESP32 publishes to this topic, all subscribers automatically receive the message. This avoids the need for constant polling, reducing network traffic and latency. Quality of service, or QoS, controls delivery guarantees. QoS 0 sends the message once without confirmation, making it fast but less reliable. QoS 1 ensures delivery at least once, but duplicates may occur. QoS 2 guarantees exactly once delivery but introduces more overhead. Event-driven callbacks on the ESP32 process these messages asynchronously, meaning the device can continue other tasks while handling incoming data. Payloads are usually structured as text or JSO, which makes parsing and command execution easier. Think about trade-offs. A battery-powered sensor may prefer QoS 0 for efficiency, while critical control commands should use QoS 1 auto for reliability. Picture this workflow. Your ESP32 acts both as a sensor and as an actuator. On one side, it publishes temperature readings to a broker topic like ESP32 temperature. The broker receives this data and distributes it to all clients subscribed to that topic, perhaps a dashboard application or another microcontroller. On the other side, a controller publishes commands, such as turning an LED on or off, to the topic ESP32 LED. Since the ESP32 is subscribed to that topic, it receives the command instantly and acts accordingly. This is the heart of MQTT, decoupling. Sensors don't need to know where the data is going, and controllers don't need to know every sensor's address. The broker handles all routing. This approach makes IoT systems scalable, modular, and far easier to maintain because adding or removing devices doesn't break the network. It simply changes topic subscriptions. Let's now translate theory into code. Using the ESP-IDF framework, the first step is to configure the broker URI. For example, MQTT broker.event.com. Next, we initialize the MQTT client and register an event handler. This handler takes care of different events: successful connection, disconnection, or receipt of a new message. Once connected, we subscribe to a control topic, such as ESP32 LED, allowing remote commands to toggle the device. In parallel, the ESP32 publishes simulated temperature values to the topic ESP32 temperature at regular intervals. To avoid blocking operations, we use free RTOS tasks. One task can publish sensor data every few seconds while another handles incoming messages asynchronously. This separation ensures that receiving commands is never delayed by publishing operations. Together, these steps mirror real-world IoT systems where sensors continuously report status and actuators respond instantly to commands, creating a responsive two-way communication loop. The event handler is the brain of the MQTT client. When the ESP32 connects to the broker, the handler confirms the connection and subscribes to topics automatically. This ensures that even after a network drop or broker restart, the device quickly resubscribes without human intervention. If the ESP32 disconnects, the handler logs this event, helping you debug connectivity issues. When a message arrives, the handler captures the topic and payload, then processes them as required. For instance, if the topic is ESP32 a LED and a payload is on, the ESP32 can toggle an actual GPIO pin to turn on an LED. This event-driven design avoids constant polling and ensures commands are handled as soon as they arrive. In real deployments, this responsiveness is crucial. Missed or delayed messages could mean incorrect sensor readings or failed actuation in critical IoT applications. Publishing data from the ESP32 to the broker is straightforward. The ESP_MQTT_client_publish function takes the topic name, payload, data length, QoS level, and a retain flag. In our case, the ESP32 might publish temperature values to ESP32 temperature every 5 seconds. Payloads can be simple strings like 23.5 or structured JSON objects such as temp 23.5 unit C. The retain flag ensures that new subscribers immediately receive the last published value, which is useful for status updates. QoS selection determines reliability. QoS 0 for lightweight, QoS 1 or 2 for guaranteed delivery. Free RTOS delays control the publishing interval, keeping it periodic without blocking other operations. By implementing this publishing loop, you simulate a real sensor continuously reporting values to the broker, which subscribers like dashboards or controllers can then consume in real time. Subscribing allows the ESP32 to receive commands from other devices. For instance, subscribing to the topic ESP32 LED lets the ESP32 listen for on or off messages. When a message arrives, the event handler passes the payload and performs the appropriate action, such as toggling a GPIO pin to control an LED. More advanced implementations might use JSON payloads, where a message like device, fan, state, on directs the ESP32 to activate a fan instead of an LED. This design can scale to multiple actuators, such as pumps, relays, or motors, all mapped to different topics. Error handling is equally important. Invalid or malformed payloads should be ignored gracefully to avoid unexpected behavior. Together, these features make the ESP32 not just a data reporter but also an intelligent, remotely controlled actuator within the IoT ecosystem. As IoT systems grow, structuring topics and payloads becomes essential. Instead of using flat topics like ESP32 temp, adopt a hierarchical convention such as greenhouse or zone 1 temperature. This allows clear organization when multiple sensors and zones are involved. Payloads often work best in JSON format, where you can include multiple fields, for example, a temperature, 25.3, humidity, 60. Subscribers then pass only the fields they care about. Standardizing your payload keys, like always using temp for temperature, ensures consistency across devices. This standardization allows dashboards, analytics tools, and controllers to scale easily without rewriting parsing logic for every device. Structured topics combined with JSON payloads enable flexible, modular, and future-proof IoT systems. As your network expands from a single ESP32 to dozens of devices, these practices prevent chaos and keep communication both efficient and intuitive. Over years of experience, I've seen developers hit the same pitfalls repeatedly. One common mistake is mismatched topic strings. Remember, topics are case-sensitive. Pay close attention here. ESP32 LED is not the same as ESP32 LED. Notice the difference? The first one uses capital letters, while the second one is all lowercase. Computers are case-sensitive, which means even a small mismatch like this can break your code or path. So always double-check your capitalization. Another frequent issue is forgetting to initialize GPIOs before reacting to incoming commands. This causes silent failures where the ESP32 receives data but cannot actuate hardware. Using unnecessarily high QoS levels, like QoS 2 for simple sensor updates, can waste bandwidth and slow down communication in large networks. Always include reconnection logic because networks drop and brokers restart. It's a fact of real deployments. Finally, resist the urge to overcomplicate early. Start with simple payloads like plain strings. Once everything works reliably, expand into JSON, multiple devices, and structured topics. These best practices make your system robust, scalable, and easier to maintain in the long run. Debugging MQTT on the ESP32 starts with monitoring serial logs. Every major event, from connection to message reception, should be logged. This provides immediate feedback on whether the device successfully connected, subscribed, or received payloads. Adding detailed log statements, like printing the topic and payload on every incoming message, helps confirm correct routing. Desktop tools such as MQTT Explorer or HiveMQ web client are invaluable for testing. With them, you can publish test messages, verify topics, and confirm QoS delivery. You can also connect multiple clients simultaneously to ensure the broker distributes data correctly. Testing under real conditions, such as with intermittent Wi-Fi, reveals whether reconnection logic is working as intended. Debugging may seem tedious, but it's the step that transforms theoretical setups into robust, production-ready IoT networks. Once you've mastered the basics, it's time to extend your MQTT project. Start by simulating multiple sensors, temperature, humidity, and light, each publishing to its own topic. Then, expand your subscriber logic so the ESP32 can respond to multiple actuators. For instance, a JSO message like device, pump, state, on, OO can control a relay, while another message toggles a fan. For visualization, integrate a lightweight web server on the ESP32 to display real-time sensor data in a browser. To support analytics, log incoming MQTT messages to an SD card, enabling offline processing. Each of these mini-projects strengthens core IoT skills, handling multiple topics, parsing structured payloads, and working asynchronously with event-driven callbacks. These are exactly the capabilities required for advanced systems in smart homes, industrial automation, and environmental monitoring. In this lesson, you learned how to configure an ESP32 as both a publisher and subscriber in an MQTT network. You explored the fundamentals of topic structuring, the role of quality of service levels, and how event-driven callbacks ensure real-time responsiveness. You also saw how to implement practical features, subscribing to topics for control commands, publishing sensor data on regular intervals, and using free RTOS tasks for non-blocking operation. We addressed common pitfalls, debugging strategies, and best practices for structuring payloads and topics to support scalability. Finally, you explored mini-project extensions that bring these concepts closer to real-world applications, such as multi-sensor systems, actuator control, and data visualization. With these skills, you're ready to design robust, scalable IoT networks where ESP32 devices communicate seamlessly and reliably, powering the next generation of automation systems.